Today what we're going to have a look at is what we mean by homologous series and functional groups. Well spotted that I missed that one out. Okay, and we're also going to look at what we call stereoisomerism. Okay, I think we might, which one will we do first? Functional groups and homologous series is pretty easy, so we'll just start with that. It's more of a definition than an actual huge amount of teaching, okay? So here we go. Cool. Okay, so I'll ask you first, what do we mean when we say functional groups? Ahmed.
It's like, alcohols, like they have their own, the functional term is like OH.
Okay, so it's basically like a little, like alcohol. So alcohols have an OH group. That is their functional group for the alcohols. Okay? Ziad, were you going to add to that?
No, I need a new book.
Oh, that's thoroughly exciting. I'll get you a new book. Did anyone else have anything to add about functional groups before I do anything? Okay, so the nice one that Ahmed picked is the OH as the functional group of alcohols. Okay? So, let's define it on the board. Okay, so functional groups are basically parts of a molecule that will always have similar properties. So they're usually like a small group of atoms. Sometimes it can be just the bond. Okay, so if we go through a couple of different functional groups, you'll see. Yeah, we already know this one, don't we? From alcohols. So the functional group there, we would call it a hydroxyl group. Then yesterday when we were talking about, what were we talking about yesterday? Nomenclature. So we had Cl, Br, I, so we've got our halogen functional groups. So they're halogens. We can have slightly more complicated ones. This is always a good one. This group at the end of a molecule. Does anyone remember what that is? It's a carboxylic acid. Good, thanks, Nee. Carboxylic acid. This one's quite important as well. It's not necessarily a group of atoms, but it is about the bond. Alkene, okay, that's the alkene functional group. Good. Excellent. And more besides, I could keep on going with that. You don't need to know too many more. Okay. what I would never say that an alkane is a functional group. An alkane is just, a chain with only single bonds in it. Hopefully that nobody else would call it a functional group anywhere else and start to try to confuse you. Okay? But yeah, so those are the main functional groups we come across for year 12. There's quite a few more in year 13. It gets far more fun. Organic chemistry by then, okay? You're going to love it. It's true. So, following on from functional groups, then we get homologous series. And again, this is something from GCSE as well. What do you remember about what is a homologous series? How would you describe it, even? Oh, it's a Thursday afternoon and everybody's quiet. Nobody wants to talk to me. Alkenes, you're the only person who wants to talk to me this morning. This afternoon, even. Go on.
I think it's like part of economy, right? No?
Yeah, exactly. It's a homologous series is like a family of compounds that all have the same functional group, or alternatively, they all have the same general formula. Okay? So I'm going to rip this off the board straight away. Hopefully you've had a chance to have a look at it. So homologous series are basically families of molecules that have the same functional group or groups and the same general formula. So let's get you doing something, because nobody wants to use their brain yet this morning. We do. Okay, something to get your brain just working a little bit. So draw and name the first 5 members of the homologous series of alcohols. Don't look so scared. Shouldn't be that difficult. All right, so we've got those first 5 members done, okay? I will draw a couple of them up, but what's the first one called? Methanol, exactly. Second one? Ethanol. Third one? No. Not just propanol. Depend how you drew it. What should it be? Propan 1-ol. Okay, because you can also have propan 2-ol. Yeah, I assume that most of you went for propan 1-ol on your drawing. Be careful. Go on.
So what if it's on the end?
If it's on the end, you still have to name it 1. Okay?
So why isn't it named buton 1?
It would be. So the next one after propan 1-ol would be what? Butan 1-ol. Okay? You must give it the number. And then if you did the last one in the same way, it would be pentan 1-ol. Exactly. Okay? Be careful. Make sure that if you feel it's needed, you put a number on. Okay? If a number's not needed, you don't need to have it. Okay? For example, methanol, there is no point calling it methanol because there's only one carbon it can be on, the OH group. So there's no point of the number. The same goes for ethanol because it doesn't matter which carbon it's on, they're both at the end. Okay? So you could just flip it around and it would still be exactly the same. But once you get to 3, you need to put numbers on. Okay? And that's generally the case for most things. You're going to need to put numbers on when you get to 3, sometimes 4. Okay? We'll see as we keep working through all these different families of compounds. So just be careful. Oh yeah. What about a general formula? Can we make a general formula for alcohols? So CN, yeah, that's always a good start. H2N plus 1, OH. Excellent, okay. That would be the general formula for alcohols, okay. And that would actually also work if you had propan-2-ol or butan-2-ol. It would still be the same general formula, okay. Good. So in that case, I told you there wasn't much to this. That was like 20 minutes worth of work at the most. I wanted to go on to have a look at stereoisomerism next. Okay, we've done our structural isomerism. Stereoisomerism is a little bit different. Has anyone actually heard that word before? Stereo. Stereo. Yeah. What does it mean? Stereotypes. Okay. Yeah. You've got stereotypes. Anything else? Something old. It is quite an old word, to be fair, and I guess these days most of you probably don't have a stereo at home. Okay, when I was young, 60 years ago, when I was young, how is that funny? What if? What if? Do you think I'm 60 something then?
No, I thought you were younger, like 40, 60 something.
Okay. I think now it's time to stop digging the hole and trying to work out how old your teacher is. Anyway, when I was young, a couple of years ago, I had a stereo system in my bedroom. We had a stereo system in our front room as well. Okay, it's what we used to play music on. Yeah, back when people, in fact, even before people used compact discs, CDs. Yeah, we used to use records or cassettes. Yeah, nowadays people are using vinyl records again because they're really quite cool. But the stereo was about the sound. It was about the sound coming from two places at once, two speakers, and the sound can be slightly different from each speaker, and it makes you kind of think that the sound is all around you. Yeah? So stereo actually means really any effect that can happen in sort of 3 dimensions. Okay? So stereoisomers, I'm getting there very, very slowly in my story. Okay? Stereoisomers are isomers that have the same molecular formula. They would actually have more or less the same displayed formula as well. Okay, but they have a different arrangement in space. Yeah. The first type of stereoisomerism that we are going to look at comes about with alkenes. Okay, because there's something very special about a double bond compared to a single bond. All right. In fact, if I give you these modelling kits, I just put one on each table. I'm sure that you can make this. What I want you to do, just make 2 models, if you can, in the group. One model of ethane and one model of ethene. So ethane and ethene. To make ethene, you need the double bonds. You need the flexible double bonds. Okay? To make a double bond, you need the flexible one. So, model of ethane, model of ethene. Ladies, we're going to... Yeah? So one ethane, one ethene. We want to see what the fundamental difference is between them. Okay, have you got there yet? Come on, one ethane, one ethene. Shouldn't take too long. Thanks. Exactly, you need two of the flexible ones to make a double bond.
But you guys are doing the one without the double.
Okay, got it? Can I borrow? Can I borrow that one? Okay. Having a look at these just for a moment. You've got your own ones as well. Okay, yes, there is something different about them in that they are different molecules. One has a single bond, one has a double bond. They're the same length. There's also a really big difference about these as well. Okay? Something that a single bond can do that a double bond cannot do. And it's actually illustrated really well by the model as well. Can anyone work it out what it is?
I think it's the angles between the hydrogen.
Yeah, actually you're right. There are different bond angles. Okay, the bond angles in here, in the tetrahedron, 109.5 here, there's only 3 sets of bonds, they'd be 120 degrees. But more than that, there's another difference as well. I can show it with the model and then you'll guess exactly what I'm talking about. If you look, what can the single bond do? And the double bond can't do. Go on. All right.
The single arrangements of hydrogen bonds can change.
Exactly. So the single carbon to carbon bond can rotate. Yeah. A double bond is stuck in place. It can't rotate. Okay. This is what leads to our first type of stereoisomerism. In fact, the only one we're going to learn about this year, which is what we call geometric isomers. Okay? Because a double bond is stuck in place, we can end up with what we call a geometric isomer. What I want you to do, hopefully you've got them in your kit, if you take your model of ethene, you should have, doesn't really matter what you use to be fair, take 2 of the hydrogens off. If you've got 2 green ones, put 2 green ones on. Okay, swap them around a little bit. So take 2 hydrogens off and put 2 green ones on. If you haven't got green ones, just pick 2 of any colour, it doesn't matter which. Okay, good, pop them on.
I have a question, sir. What's the significance of it being like?
You'll
You said
see in just a second, the rotation is important. Or the lack of rotation is very important.
Yeah,
But it means that if this rotates,
yeah.
then all of it doesn't matter where you put a slightly different atom on there, it's always the same.
Yeah.
Yeah?
But then what's the like what I don't know how to ask the question, but I mean like if it looks the same in any plane, then why
Nice. Okay. Did you check? Oh, brilliant. Let me take that one. Awesome. All right then, folks. Fantastic. I knew if I gave you this task that we would end up with two different isomers. Okay. I don't know if anyone can see the difference between these. Okay. It would be ideal if they were like both of them were green, but just imagine in your heads that on the one that's blue, they're actually green bits. Okay. Those have exactly the same bonds, double bonds. Okay. They've got the same two atoms as functional groups. All right. But what is the difference? Can you see the difference between these? Okay, how would you describe that there's a difference in that case, Kumar? What would you say? Okay, one is on top, one is on the bottom. Yeah, that's kind of one way to describe it, definitely. Ziad? Possible, yeah. But let's just take it with these two for now. Okay, we will carry on with what you're just saying. Okay, so you can see, hopefully, Leah, you with us? Good. Okay, on this one, both of the chlorine atoms are on the same side of the double bond. On this one, they're on opposite sides of the double bond. And they can never be the same, because I can't get this double bond to rotate at all. So they're not going to be equivalent to each other. It's not going to spin. We end up with this, geometric isomers. Okay, it happens when we have two different groups, okay, on either side of carbon atoms, okay, and even more than two groups, you can have the same thing, which we'll see in a second. Okay, can you physically see the difference? Yeah, it's really important that you can see that. There we go. That was your one, and that was your one. Perfect. All right, so. Okay. So, definition first of what a geometric isomer is. So these isomers have the same bonds and functional groups in the same place, but the groups are arranged differently around the carbon-to-carbon double bond. Okay, if I do it here, you can probably see it easier, maybe than me holding it up with the model. Go. So those are two isomers of 1,2-dichloroethene for a start. That's its name. But they are arranged differently in space. This one has both chlorines on the same side of the double bond. This one has it on opposite sides. Okay, we've got a word for that, in fact 2 words for it. One to mean on the same side, one to mean across the bond or on different sides. Okay, they are cis and trans. Okay, cis is on the same side, trans is across. Okay, I'm sure there's other meanings that I could get for trans as well. Let's not go into that. Probably best not to. So, we said that this was one, 2-dichloroethene, and again, same. But this is cis, and this one is trans. Okay.
So is there even like more specific like naming to them after this one? Like,
There is something else we can do. Okay, which is exactly the same with geometric isomers, because this is kind of a simple case of having geometric isomers. Okay, I'm just going to let you finish off the notes on that for just a sec before I tell you. So cis and trans really only works when you've got 2 different groups like this around the double bonds. But if I had 3 different groups around the double bonds, cis and trans doesn't really work. We have to go up a level, okay? In fact, I swear when I learned chemistry, however many years ago, let's not go into that again, that there was only cis and trans. In fact, I'm sure when I started teaching, there was only cis and trans. But now they've come up with something called EZ, okay, which is just a different way of looking at exactly Z. That was the face that I pulled when someone told me that there was EZ. I was like, what? What are you talking about? So I'll give you the example right here, okay? Is everyone happy they've got this little bit down? Yeah? Okay, Gabby? Good. Shout if you are not okay at any point. Okay. So we can, rather than just cis and trans, we can call them E and Z. If we consider this one for a second. Yeah. There we go. Oh. Just trying to work out what to call this at the moment. It's like 1 bromo, 2 chloro, 1 fluoro, ethene. Keep the numbers low, put it in alphabetical order. But can you see the difference for a start in the 2 isomers? Yeah? All I've done is I've switched around these 2 here. Okay? There the Br is on top, here the F is on top. So all I've done is switch those around. Kumar, you still with us? Good man. Okay? But cis and trans doesn't really work with that, because I've got all of these different groups. I can't say that one group is across the bonds, because I've also got this. I can't say that that's on the same side of the bonds, because I'm not taking this into account. So So it gets really complicated. So that's why we came up with EZ, allegedly. Okay. What we need to do is we need to give each of these groups a priority. Okay. And essentially it is the heavier atom gets a higher priority. Okay. So what we need is the atomic number of all these groups that are not hydrogen. Okay, we know the atomic number of this is 1 and it's going to have a really low priority. But if we've got the atomic numbers of all of these, we can work out how we're going to prioritize them. So let's have a think. We've got Cl, then we've got Br and F. Okay. The atomic number. What's the atomic number for chlorine? Someone tell me. Atomic number? 17, thank you. Okay. Bromine? 35. Fluorine? 9. Okay, so we worry about what is on. We worry about looking at the priority, the highest priority on each side of the double bond. Okay. So in this one, what is the higher priority, chlorine or hydrogen? Chlorine. It's got the highest atomic number. Okay. Which one has got the highest one here? Bromine, exactly. Okay. And so the priorities are exactly the same here. There you go. Okay. Now we've got to work out what E and Z actually mean. Okay. They come from German. Does anyone know German? James does. Ahmed does as well.
I don't know, but I know what you mean.
Okay. The easiest one to remember is Z. Okay? Because Z stands for same side. Doesn't really. Okay? But it's the way to remember it. Okay? Because Z is on the same side. Okay? Or same side. So you remember. See what I did there? Okay? The other one is E. Okay? So this is Z, like this. This is E. Okay? Z for same side. Okay? If you can remember that. And then E is for the opposite sides. But you only need to remember one of them, don't you? Okay? They actually mean in German, if I get it right, zusammen, which I think, see, you know a bit of German as well. Means together, apparently. And then, don't know if you remember this one from your German. I love the pronunciation. Entgegen, which I think means opposite in German. Okay? So that is how we remember. Fantastic. I think we need to do a little bit more on this, but I'm going to give you, I know you're doing a bit of revision and stuff for your homework, but it's about time I actually gave you proper homework to do. All you got to do on the sheet, there's 2 of them, there's only a little bit on the second sheet, is work out what kind of isomerism, if any, and give some reasons, okay? So that's your homework to complete. I'll put it on, show my homework for you.